Welcome friends, let us try to learn about the basics of Bode Plots today. As we are going through the frequency domain analysis of control systems, Bode Plots are another set of tools which we use in the analysis of systems to frequency domain, and it is very convenient. So this is a textbook. I generally refer to this textbook by Professor M. Gopal, and other two reference books are these. You can make use of these books as per your convenience. And the overview of today's lecture: for Bode plots, we need to learn what is gain of a system, what is phase of a system, and how frequency plays the role. And the magnitudes of gain, phase, and frequency play significant role in drawing the Bode plots. The range of all these quantities are very important in system analysis. We need the semi-log plots to draw the Bode plots, so we need to learn what are the semi-log graph papers and the significance of semi-log graph papers for our requirement. So let us start with the gain of a system. We can take the simple example of a system, say G at j omega is supplied with certain input, say R, at a given frequency, and the output is recorded at the frequency. So if the input is say 2, a constant value, and output is 5, so the gain of the system is y by r is 5 by 2 is 2.5. But if the input changes to 4, and I am assuming that system is linear over the frequency, so it should give another gain, that is 10, but here again it should be 2.5. So we see that if the system is behaving statically for a given input frequency, so it is wise to analyze the system gain than analyzing the output. We can understand how better the system adheres to its input at a given frequency through its gain. So that is why we study the gain, and whenever we are applying gain at some time t equal to 0, output may appear at after some time, maybe 1 millisecond. So this delay will basically determine the phase of the system. So if you know the frequency omega, then the phase of the system is omega t. So that is how we can determine the delay of the system. And all these physical quantities are measured across a range of frequency of our interest. So frequency varied over a range, and we study the behavior of the system, how good or bad the system behaves for this range of frequency. So what are these units of different quantities? Let us see one by one. We first start with the gain. So in case of system analysis, not only control systems but in electronics communication systems, or where the sound plays the important role, basically this unit of gain is obtained in terms of certain quantity which we define as decibels, but it is again derived from the name of the inventor, Graham Bell. So how do you find out the gain of a system for Bode plot? So we have the magnitude. Suppose the system has a magnitude, we write simple as G. So its magnitude we are taking at a given frequency, and this gain is actually giving you information about the energy of the system. So if I am measuring the voltage, so naturally I have to square the voltage to get the information about the energy of the system. So I am doing gain square taking logarithmic base 10 because the range is very large. So I am converting into logarithmic scale to reduce the size of the plot which I am going to draw on the graph paper. Now this quantity will basically give a very insignificant change in the energy content of certain quantities like sound. So to overcome it, we multiply it by some multiplier 10. So this will give you the magnitude. So this is basically equal to 20 log base 10, the magnitude. So now if 10 is not there, this is just bells. And if 10 is multiplied, this is decibel. So we write it in short as decibel. Now again the frequency and time can be connected to get the phase delay of the system. So we can simply use for phase the unit degree. You can use radians also. But whenever we are plotting a graph and we are writing in the terms of radians, it is little ambiguous to understand what is the actual scale of the change of certain results. Rather, degree will give us a better picture. Now the frequency is measured. It can be measured in hertz, but in practical situation we use radians per second. So radians per second will give you a better picture of the analysis again. So we see how it comes. When we are trying to plot it, so we use the semi-log plot. Here you can see that these different bars are at uneven spacing. So what we have done, actually we have kept the x-axis on logarithmic scale. So the frequency I am using here is directly in radians per second, but whatever frequency I am keeping, it is automatically converted into logarithmic scale. I start here, suppose say from 10 power minus 1 radians per second. So this is actually 1 into 10 power minus 1, this is 2 into 10 power minus 1, this is 3, 4, 5, 6, 7, 8, 9, 10, like that it will go. So again it becomes 10 power minus 10 power 0 radians per second. Similarly we go up to 10 power 1 according to this range. We are giving with this range, it can be increased. So in a practical situation we vary from 1 power 100 radians per second to 100 radians per second. That is sufficient for control systems. For electronics or communication system, that may vary, it may be a bigger range, but for control systems, because these are low pass systems, so this range is sufficient, and we can actually design the linear range of operation of most of the systems within this range. So here I am having the y-axis in terms of magnitude, which is 20 decibels, 20 log base 10 magnitude, that is in decibels. This is in decibels. So this is giving us the magnitude. Similarly, 10 power minus 1, 10 power 0, 10 power 1. So I can have the phase over here in degrees. 0, 90 degree, minus 90 degree. This is the phase. So here, because on y-axis I can see that the magnitude has been converted into logarithmic scale, so here its linear scale is sufficient for us. If it is directly magnitude you are using, then its range will be very high, you cannot accommodate within the plot on your paper. And phase is basically it is linear, so there are no issues on this linear scale. Let us see in more detail how the plot will be seen in case we are using computer output, say MATLAB. So in MATLAB, if you see, you can see that this is the magnitude. So you have the magnitude over here, you have the magnitude over here in decibels, and the phase, it has been taken in radians. Here you can take in degrees also. This is the frequency scale. You have taken the linear scale, but automatically it converts into logarithmic scale. So 1 into 10 power minus 1, 2, 3, 4, 5, 6, 7, 8, 9, then 1 into 10 power 0. 10 is 1 into 10 power 0. So again we can get 1 hertz, 1 radians per second. This should be given, the unit should be given as radians per second. Radians per second. 1, 2, 3, 4, 5, 6, like that, 9, 10. So it will become 10 radians, then 11, 12, like that. 11, sorry, 10, then 20, then 30, up to 100. So you can make this range bigger. Even you can make a bigger range from this. So let us see further what is a practical example of such a plot if we draw the Bode plot, because today we are just having the introduction. The Bode plot of a practical situation, you can see the magnitude over here. You can see a change in the magnitude, a sharp change in the magnitude over here. So maybe this is 10 decibels. So 10 decibels means, if you take the antilog, means 10 equals to 20 log base 10 magnitude or gain. This is actually your log of base 10 magnitude equals to 1 by 2. So you can understand that if you take the antilog of this, you can get the magnitude. Now this quantity is a change, means increase in the value of gain, and here you can see the how much fall in the magnitude is minus 60 decibels. So minus 60 decibels equals to 20 log magnitude. So this becomes minus 60 by 20 equals to log magnitude. So if you take the antilog of this, you will see that the magnitude will come in fractions. So the range between this and that cannot be plotted on linear scale, so you need to take the decibels. Similarly here in the phase, it's a linear scale, so there is no issue in plotting it on the linear scale. You can see it varies from 0 to minus 270 degree. So that is how we plot the Bode on graph paper for different system responses over a range of frequency. So this information is given just to introduce our Bode plots, and in the next lecture we will start by talking about what are the different transfer functions for which we can draw the Bode plot, and what are the different patterns of the Bode plot we will see for type 0 first order system, then for integrator, for differentiator, then the inverse of the type 0 first order system, then the second order system, how the different Bode plots can be plotted. So this much is for today. I am again advising to subscribe for my students and set the bell icon so that you can get the uploads regularly. You can ask me queries through my email ID controlsystemsfaq@gmail.com, and queries can be sent to me through WhatsApp or call also. Thanks for your patient listening.